Very good. Well, it's about the top of the hour now, so we'll go ahead and get started. We have a good number of people joining us, so thank you, everybody. Welcome on this lovely Tuesday morning, afternoon for some of you. Thanks for joining the Petasense user webinar. This is the first time we're doing this, and we've invited one of our clients on board to kind of talk about their experience with Petasense and the implementation of the wireless predictive maintenance system. So some of the folks in here are joining us from either current clients or prospective clients, and I'm glad that we got everybody here to learn a little bit more about Petasense. So today's presentation will be given by Arizona Public Service, and we'll have two speakers from APS today, Don LaMontagne and Laura Benbrooks. Without further ado, I'll go ahead and turn it over to Don, and maybe if you'd like to introduce yourself, Don, and Laura as well, and we can go ahead and get started.
Yeah, I'm Don LaMontagne. I'm the supervisor for equipment reliability and asset management here in APS fossil generation. I was previously the asset manager in our T&D division for about 13 years, and also have about 17 years of nuclear power background. So I kind of talk about the triad of electric utility business. I've kind of got all three legs, if you will. And I'll let Laura introduce herself.
I'm Laura Benbrooks. I'm a predictive maintenance engineer here at APS. Prior to this, I worked for Alcoa in Texas, also in the same field. I have a maintenance and production background, and prior to that, I was in the Navy.
Great, thank you for the introductions, and we'll go ahead and just jump right into our presentation here. So Don, why don't you go ahead and kick things off?
All right. So just a quick intro about Arizona Public Service. We are the largest electric utility in Arizona. Been in business over 130 years. We do own about 7,300 megawatts of generation and serve about almost 1.2 million customers in most of the counties of Arizona. Again, we have 11 generating sites, primarily natural gas and coal. And we also operate the largest nuclear power plant in the country, which has also held the record for most megawatt hours generated in the whole nation since about 1992. So our portfolio, we consider it to be well over 50% carbon free between our solar portfolio that we have as well as our nuclear power. Our focus of this presentation today is going to be on our Sundance generating station. It's a 450 megawatt natural gas fueled power plant. There are 10 units that are simple cycle. They're in 5 power blocks. By that we mean there's a common step-up transformer, generator step-up transformer. And then there's common facilities within each of those 2 units, things like the combined water system and such, lube oil systems and whatnot. The unit itself is about 52 miles south of the main Phoenix Valley here, and it's typically unmanned and remotely operated from a power plant in Tempe. The reason why we chose Sundance for our initial installation of the Petasense wireless vibration monitoring system primarily centers around the entry into the California ISO's energy imbalance market late in 2016. Prior to that market entry, Sundance just fed APS's load with peaking power. So it was used maybe about 10% of the time throughout the year. But on entering the energy imbalance market, the units were designed from a previous merchant power company had designed them and built them so that they could feed into the California market quite easily. And we acquired the plant in 2005. Again, we just use it for peaking between 2005 and 2016. Well, in 16 then, the number of starts tripled and the run hours doubled because the units are priced very well for the type of load it's trying to serve in that energy imbalance market. So there is a lot of solar, obviously, in California and in the Southwest. And before the sun really peaks during the middle of the day, there's a lot of load with people getting up in the morning. And again, there's also load in the late afternoon with people getting home and cooking dinner and things like that. So there is need for rapid ramping units on what we call the shoulder hours of the solar generation. And because the units then were used much more extensively, we had immediate concerns with what's the reliability of these units going to be now that we're using them so frequently, and how are we going to get good data to better optimize our preventive maintenance. So reliability again was foremost in our mind for these units with the amount of work they're now getting. The other problem with being so far away from the valley and running basically during those shoulder hours is there's typically not people down there during those times that the units are running. So getting data, vibration data particularly, you need the unit running. And so if no one's there, you can't get the data. And the other reason we looked at a system such as this is that wiring sensors is very expensive, and as well as adding conduit all over the plant. So we're looking for a way of getting a system in place that can fill in for our infrequent data gathering, but also be fairly cheap to install. And the result, what we're trying to address obviously was the unplanned downtime during our peak, and costly and tedious repairs, and any kind of unnecessary PM. Typical asset management type of concepts. You want to try and maximize your dollar, sweat your assets, et cetera. So in order to do that, though, you need good information about what the asset's doing. So our ideal system was going to be something that was going to be cost effective, but also take data fairly frequently. We didn't necessarily need it to be continuous online monitoring, but something on a periodic basis was acceptable. And we wanted to minimize the amount of conduit that we had to go install. Anytime you're starting to run conduit on a power plant, you're adding dollars to your project quite rapidly. It had to be security compliant. We didn't want this to be a SIP system. We wanted to stay outside the SIP world so we didn't have all those headaches. In order to do that, though, one thing you got to remember is you can't have this data going to the control room where a control operator can take action off of an alarm. So we use this system only with our maintenance folks and our engineering staff. That keeps us out of the SIP world. Not to say that the security protocols were, they were well vetted by our IT group, but by doing it this way, we have minimal IT resources that we need, and again, it leaves all those NERC SIP headaches outside. We also needed a robust system because we're in a very hot part of the country, and we're in desert climate, a lot of dust, dirt, heat, etc. And we needed to take that into account. And then we want to be able to transmit wirelessly from around the plant, and then from the plant wirelessly out to, say, a cloud-based solution. So this is kind of the plug and play in IIoT, for you not familiar with the acronym. That's the Industrial Internet of Things. So basically, we've got wireless sensors on the pumps and motors and some fans. There's also some wireless transmitters out there. We have not used those yet, but we're getting ready to go give those a trial as well. But basically, the wireless sensors you see in number one there of the slide, basically they're glued on, and Laura will talk about that a little further in her portion of the presentation. They basically are on multiple ends, the inboard and outboard end of motors and pumps and such. That data then is collected through a wireless network, which is where I'll predominantly talk about today, is how we get the data into the network and then out to the cloud. And from there, the cloud, we have utilization of a number of web and mobile applications to go analyze the vibration data itself. So here's the actual implementation. Go to the next slide as well. That's a little picture there of Sundance. So what we have basically is about 100 rotating assets at Sundance. And the listing you see there is the typical pieces of equipment. If it says unit, that means we've got 10 of each. If it says power block, we've got 5 of each. And in the common facilities, we have typically 1 of each, although there's some redundancy in some of that common facility. But basically, it's a 10, 5, and 1. So you can kind of do the math there a little bit, but basically over 100 rotating assets that we instrumentated. So the basic Wi-Fi network that we've implemented, you can see the Wi-Fi tower in the background. That's where we're trying to shoot our signal to. So we've got a cellular gateway, along with an access point router, which collects the data from the mesh repeaters that are throughout the site. And the mesh repeaters are located relatively close to the vibration motes and transmitters themselves. So I think the next slide gives you a layout of the plant. So we've got about a 500,000 square foot footprint here, and you can see the different dots on here. Now we've got, I don't know how to call out this color. Let's call it a kind of a beigey color is the repeaters, and there's a dozen repeaters throughout the site. And then the light blue color is where the gateway and the access point routers are located. And you can see there's two ponds, one on the east side, one on the west side. We've got wireless sensors on pumps in both those ponds, as well as close by to where the units are themselves. The one repeater on the south side of that diagram, that's where most of the common facilities are. The next slide will show you, we make a hop from Unit 10's stack over to the RO pond to the right, about a 500-foot direct line of sight jump. So the Wi-Fi signal is quite good throughout the plant. This is what one of the setups look like, or a couple of setups, I guess. The left-hand side, you see the box closed. This is where the access point and the gateway is housed. You can see the two antennae on the top. You see a couple in the middle photo. You see the insides of the box with the two fans to help keep forced cooling going through the box. These boxes are a fiberglass reinforced polymer, so they don't attenuate the wireless signal at all. There's also, you can kind of see in the bottom left of the middle photo, there's 120 volt power inside the box. So they're nice boxes that came straight from a manufacturer that had the 120 power in it. It's got a nice backplane for mounting your brackets and training all your cable on the inside, and has the powered fan. So it's a nice setup. They have a nice bracket situation on the backside, and we just basically screw them on, or with the bracket to the lighting pole that's up here. Now you can see where we're at here on top of, or not on top of the stack. We're about halfway up the stack at about a 45-foot elevation, and from here we got a nice signal looking down on the units. The one on the right is a smaller box for one of the repeaters. That's on one of the enclosures on the common area. But very clean installation. You see a little bit of conduit coming outside the enclosure there. This building here is for our fire pumps, and they're on the inside. The power was on the inside of this building, so we just ran a short length of conduit on the outside to get the box on the outside to get a good signal back to the access point. And you can see we've got I call 5-bar signal strength across the entire site. It's basically 4 and 5 bars on basically all of our machines that are out there. So quite a good signal. By strategically locating the boxes where we did, halfway up the stack, so we're looking down on the power block area of each of the units, we're able to get a very strong signal. So we're very pleased with how that implementation went. And so far we've got roughly about 1.4 million data points collected so far. Now that data point represents the fact that these sensors are a 4-channel sensor. They're full-blown triaxial sensors, so they got 3 channels for that, and there's a 4th channel for surface temperature. So those 4 data points coming through about every 3 hours is how we've got things typically set up. Pulling data now for about 6 months, we've got a good 1.4 million or so data points. That compares to if you were taking those on a route-based setup, you'd be about 6,000 route-based measurements. And I think at this point, I turn it over to Laura to help explain how the sensors are installed and configured.
Well, the sensor installation is very easy. In most cases, your equipment doesn't have to be shut down or locked out for the installation. If you take a regular vibration with portable route, it's basically the same way that you're doing. What you have is, or what I have is a small Dremel tool with an acorn grinding tool on it. You need to clean the paint off or get it down to bare metal at about a 1.5 diameter circle. And at that point, you can epoxy it in place. The sensors are very easy to install because there's 2 arrows that point towards the coupling end. There's also 3 indentations so that you cannot put the sensor on backwards, so long as you follow the simple installation instructions of following the arrows. Christian, who's from Petasense, he's from customer satisfaction. He came down to help me with the 2 installations, the 2 initial installations. When we went down to Sundance on the week of the 21st of May, and we installed 100 sensors throughout the power blocks. And power block 3, we only got half of it installed. That was our cutoff point there. But on May 30th, the pump came on, and that was our first reported issue that we had to the plant. I called the plant and reported the issue that we had, and went down a couple of days later to verify the readings with my portable analyzer, and both readings indicated the high-speed shaft of the pump had a rotating looseness in it. This is actually the Petasense reading. If you can see, the pump has ladder stages of journal bearing wear. There's evidence by the presence of the whole series of speed harmonics, the one-time speed harmonics, and rotating looseness is caused by the excessive clearance between the rotating and stationary parts of the machine. And then the plant replaced the pump, and this was the reading that we took after the pump was repaired. So you can see, as you can see, the one-time amplitude dropped significantly, and the harmonics dropped significantly also. You can see the high-frequency noise field all went down also. Since we did our initial installation, I've had 13 major defects that were caught. The last defect that we had was on power block 1, the combo water pump. On September 24th, I went out to the plant, and the plant had asked me to come out to check a different pump and motor that they were going to install. And while I was at the plant, I noticed that the combo water pump in power block 1 was cavitating, and that the suction pressure of the pumps was fluctuating. The discharge control valve was also continually exhausting air, and I reported those anomalies to the plant. Shortly after that, right around October 4th, you'll see that the machine health started taking a big drop. And you can also see that there was a vibration spike. This is on the motor drive-in. And so I called out to the plant, and you can also see it was about 3 or 4 days later, we started having a spike on the temperature. So I called out to the plant and asked them if they'd go out and check the pump and motor and see what was going on. They said that the gearbox was starting to fill up with water. And this was the readings. We're in an outage right now. We were actually going into an outage at the end of October. So they asked me if I could help them to keep the motor running until we got to the outage. So one of the other plants had a UE grease caddy, so I asked them if they could bring it down there. And so we greased the bearings with it. And this was what the reading was after we greased the bearings. And we continued doing that until we got into the outage. The outage, what we did was replace the pump, and we did a autopsy on the pump. We found out that the pump had filled with water, and that it had damaged the high-speed shaft, and there was also cavitation pitting on the impeller of the pump. So, and all that we had seen basically with our spectrum readings. What we had said was actually what happened.
Okay, I'll take back over again. So we've got a few good learnings from so far going wireless with our system. The network topology itself, you have to kind of think through. So the diagram you saw earlier, I call Plan B. We actually had a plan A, which was I thought kind of slick, but didn't turn out to work in that we had located a device that basically a pigtail, a transformer and a pigtail with 120 volt that plugs into a photo cell socket of a streetlight. And my initial plan was to install these devices on streetlights and have the major boxes with the gateway and the access point up on the streetlight that goes between there's roads that go in between each of the power block. But when we were in those positions, we found that the steel from the units themselves, we were trying to shoot a signal, if you will, between that street light through the unit to the machines and that were between the two units in those power blocks. And so all that metal attenuated the signal too much, and we were not getting a good signal. So during our site survey, if you will, I took a climb up halfway up the stack, and we had 120 volt power sitting there. So we were able to tap into that. Laura and I went down on a second trip and actually just tie wrapped devices onto railings and stuff, and all of a sudden we're starting to get our 5 bars, if you will. So again, you got to kind of map out your network topology and make sure you try and get some, doesn't have to be clean line of sight, but certainly the less metal you're trying to get signals through, the more successful you're going to be. There's also processes you've got to go and start thinking about in terms of there's battery life issues. The batteries are, depending on how often you take readings, the batteries will drain quicker. So right now we think we have them on a schedule that should last about a year or so, although we've only had them in for 6 months right now. But you got to have some kind of processes with maintenance in terms of, getting ready to start doing, if you will, PMs on the batteries for these sensors, as well as when you find issues like Laura's been doing, she's got a way of writing service requests in our CMMS so that we can get the problems to the maintenance folks at Sundance, as well as I've asked her to kind of, every couple of weeks, kind of do not a triage, but a ranking of the issues, because some are going to degrade faster than others. So they're all, all 13 of them that she's written up so far are all there, but some are going to degrade faster than others. So I kind of want to constantly keep an eye on which one's the worst one, the next one to go work. There's a limited staff, obviously, in our plants. We're all, trying to be lean and mean. So we try and make sure we keep the most important ones in front of them first, and that may be a changing list. So you have to think about some of those things, as well as, again, I got to stress again, don't send these data to the control room operator. You got to keep them out of their hands so you stay out of your SIP world. And then define what success looks like and have a long-term plan. In our case, we knew we were going to have a lot of maintenance issues from the new behavior that we're, the new way we're treating the plant being in the energy imbalance market. So we knew, and the plant was aware that we're going to find stuff. So you've got to work together with the plant so you're not making them look unsuccessful. You want to make sure that they can be successful. So again, you've got to work with them in terms of, what do they need next? What kind of information do they need? And how are we going to get them out of this short-term bow wave of work, if you will, and into a long-term plan of proactive maintenance. So did we meet our goals? Well, yes, I think we did. We have a cost-effective means of monitoring our vibration data at a remote plant that's, again, about 50 miles from our Phoenix Valley here. In basically a 6-month time frame with about 100 machines, we've already caught 13 defects and prioritized those and putting them in the maintenance queue to get corrected. The all-in cost, that's the hardware, the software, the Wi-Fi network, et cetera, is about $800 per sensor. So we think it's a very cost-effective solution. Again, we're security compliant. We're not being used by the control room. They understand that as well, that they don't want to be in SIP world either. So we've set it up in such a way. We've also, it's been vetted by our IT group and how we're doing this, and passed all the hurdles there. And it's a robust system. We went through a hot summer and didn't have any issues due to temperature. We made sure we spec'd out the right kind of communication equipment that can handle the ambience here in Arizona. That's not a trivial thing to go do. Path forward. So what's next for APS? So we've got other power plants, and next year we've got 2 more power plants slated to roll this out at. One's a 2x1 combined cycle plant out on the far west side of Phoenix, about 45 miles outside of Phoenix on the west side. And then the second one is here in town, only about maybe 8 miles or so from our corporate headquarters, but it's got 5 different combined cycles and 2 simple cycle units there. So it's a fairly large facility. So we want to get those 2. They're both critical facilities for our load purposes, and we want to get those up and running next year. We have a few more assets at Sundance we still want to try out the sensors on. And we want to look at also transmitters for some of these hard to reach assets. Laura just finished putting sensors on the exhaust fans at the Sundance units, but that required scaffolding to go install. So we want to go back in possibly next year and use the transmitters, because we won't need batteries up in an area where you'd have to have a scaffolding to go replace the battery. The transmitter can be mounted lower to the ground and make that much easier to go and maintain that going forward. We also want to get our data integrated from the cloud down to our Pi historian. We've got an enterprise-wide Pi system, and we want to have the synergy of linking that data with other Pi data that we have, pressures and temperatures and flows and things of that nature, as well as get integration with our CMMS. We want to be able to have a alert coming from the Petasense cloud. We're able to send that to our CMMS system and start generating the service request. We'll still have to have some manual intervention there in terms of filling out what the problem is and what we think the resolution is, but we want to get that going as well. And then again, next year, 2 more sites, and then the year after that, our plans are to have 2 more sites again in 2020. So we see this as an extremely useful tool. It's been able to provide us with good, actionable information from almost the immediate time we turned it on, and we're going to go forward with this at all our gas sites. We do want to go do some site surveys at one of our big coal units, our Four Corners power plant, and that one there I think is going to be a little trickier in terms of the amount of steel. If you're familiar with coal power plant versus a gas plant, trying to get the wireless signal to bounce around the coal plant, we'll probably take a few more repeaters and stuff, and that's one of the things we have on our list for next year, to go and do a site survey there to figure out cost and schedule to go and get a system implemented there as well. But can't say enough about how well the system's working so far. It's already paying dividends with fines, and as we get farther along, we'll be able to get into more proactive mode. Right now, we're just kind of fighting the fires as we're finding things, but once we get that under our, past us, we'll be getting into more of a proactive mode with what we're learning with the system. And with that, I can turn it back over to John, I think.
Great, yeah, perfect. Thanks so much, Don, Laura. Great job. I think we wrapped up a little bit early, but I think that we packed a lot of great information into the presentation, and at this point, we'll probably stick around for about 5 to 10 minutes just to take any questions here from the audience. So folks, if you can see on your Zoom panel, either at the bottom or top of your window, you should be able to enter into the Q&A section, and we can start addressing those questions. All right, so we have one question here for Don. Don, are you monitoring any equipment internal to the units? Any interference issues there?
That's one of the sensors we have to still try out. We have a lube oil pump that's inside the turbine enclosure, and it's very close to the generator, obviously. And so we want to go and try that out with just the sensor alone and see if the signal will come back out of the enclosure. If not, that's what we talked about the transmitters earlier. We may try a transmitter and have that on the outside of the enclosure and see what kind of signal we get that way. So we're going to try a kind of a plan A, plan B on that as well and see how that works. Some of the other devices are combo water pumps, other lube oil pumps. They're inside of sheet metal buildings, and again, sitting up halfway up the stack, looking down, I'll call it a God's eye view, if you will. It sees right through the roof of those sheet metal buildings, right down to those pumps and motors and stuff. And you saw the 5-bar signal, throughout the plant. So as long as you position it correctly and it's not going through a lot of what I'll call structural steel, that seems to be the key to making it all work.
Great, thanks. We have another question here. Did this site have an existing vibration program? Can you share a little bit about what you were currently doing, or sorry, previously doing?
Well, yeah, we had a vibration expectation to go do manual routes on a monthly basis on what we call the critical equipment. We do have a criticality list, and we're essentially doing those critical equipment now with the wireless sensor. But the expectation was to go try and take data once a month. But again, with the units running in those shoulder hours, that's typically about the time that people are getting to work and about the time people are leaving to go home from work. And so the opportunities weren't necessarily there to go and get the vibration data. So this affords us that opportunity to get consistent data on our critical machines, where before, because of the remoteness of the site and the fact that it's not manned, that made it almost next to impossible to get consistent vibration data in the past.
Great. All right, another question here. Are you using this to drive preventive maintenance activities or just corrective?
Well, I'll consider this a predictive maintenance tool. So in the end, it's going to be to do this as a condition-directed maintenance as opposed to a time-based. We're going to try and find things before they deteriorate to a point where the repairs on a PM task might be too expensive. So we'll start learning the sweet spot in terms of call for maintenance at this point here, so that we're not on the too far downslope. So one of the things we probably didn't highlight too well on one of the slides, Laura had a picture showing the machine index or the health index for the machines. So we're starting to use that and trying to fine tune those health indexes that the artificial intelligence in the cloud can assign to the machine. So we're going to try and leverage that information more in the future. Once we get out of the firefighting mode with all the things we're finding right now and getting in a proactive mode, we'll be using this as a condition-directed approach rather than we'll probably back off on some of our time-directed tasks at that point.
Perfect. All right, well, we have about 3-4 more questions. We'll just close out on after those. Next question is, have you estimated cost savings on the 13 faults?
Not yet. We don't really have a good setup yet to go do that. We're working with our GADS folks to try and get estimator up and running, that we can start getting a better number, if you will, from true market conditions, if you will, because these units play so much in that California ISO market. A lot of this savings is in the lost generations hours, megawatt hours that we save. So we need to get that up and running with good, accurate values, because in reality, the lost opportunity generation cost, or perhaps in some cases penalties that we get from the market. If we say this machine's going to be up and running at this time and it can't do that, then we could pay penalties as well. So that market cost and savings dwarfs the corrective maintenance cost. So that's really the important driver here, is getting that up and running. So right now we don't know, but we will have those numbers in the future. But we do know from kind of just seat of the pants, back of the envelope kind of calculations, that the lost generation and the penalty costs are definitely dwarf the corrective maintenance cost.
Yeah, perfect. All right, next question here. Do you have any plans to monitor strategic valves?
We've talked about that a little bit. One of the problems that Laura mentioned, we have a cavitation issue on some of these pumps down there, and one of the valves seemed to possibly be the culprit. We've got it scheduled to come out on the 23rd, and we're going to do some forensics on it. And if it turns out that valve is actually the culprit, then we may talk about doing some, future transmitters on some of the valves, at least get a sense of, we think this valve might be cycling somewhat when it shouldn't be. So we think some of these transmitters and sensors can detect some of that vibration of the valve opening and closing, and that may be an effective and cost-effective way of detecting that failure mode in the future.
Got it. Okay, got a couple more questions here. Do you plan on feeding this information into your PM program, potentially optimizing frequency and task selection?
Yes, we want to use this more as a condition directed as opposed to a time base. So we will have, and that's a lot of work we're going to be doing next year, is using doing some preventive maintenance template work for our assets. And so this will be part of that strategy as to do more of a condition-directed follow-up on what we find, as opposed to doing an overhaul every X number of years or something of that nature. We're going to try and use this more and leverage that because we think that'll be a more cost-effective route as to do this condition-based approach.
Okay, great. And we'll just take two more questions. I think there's a couple of questions being asked that are a little more broad to the Petasense system in general. So I'll definitely get back to your individual questions about the Petasense system individually. But we'll take two more questions here for Dawn. So one is, since implementing without having to send data, or sorry, send people to the assets to gather vibration data, is there a percentage that you know of that you've been able to gain back in those people's resources time?
Well, that's the kind of the funny thing about Sundance is because people were not able to get down there when things were running. They basically were not taking the data. I think at some point they just, Einstein's description of insanity, doing the same thing over and over again, expecting a different result. I think they finally just realized they're not going to get down there to take the data, so we're just not getting data. So there really isn't a resources gained in this case from the terms of people going and taking the data because they weren't able to do it. Now, the next two sites that we go do, there are people on site. They are manned sites, and we should see some savings relative to that. We don't have, obviously data on that yet, but in the case of Sundance, it's just so unusual in that it's unmanned, an hour drive away from town that, it just was not getting done. And so this was our way of making sure we started getting data that we can start maintaining this plant better. So yeah, there's really not resource savings, but you should see that. It's a good question. You will see resource savings on a manned site, and we expect to see that on the next two sites that we go do.
Great. All right, and we have one last question for you, Don. How do you determine if the repairs are not being corrective maintenance? I guess the question is around how do you determine if it's predictive, catching a defect predictive maintenance wise, or just a standard PM that you're catching?
Well, we have in our CMMS, we have a term we call condition directed maintenance. So that's kind of what we're tagging these things to is condition directed. So that's kind of a sub work type that we have. So it's considered a CM, a corrective maintenance work order with a sub work type of condition directed. So we can segregate out our finds from the online wireless vibration from other typical PM type work, or just something that failed on its own without us catching it. That would just be a CM without the condition directed sub tag on it. So we do have the means of segregating out what we're finding, and we'll be reporting on that in the coming months as we're working on getting those added into our system health reporting.
All right, perfect. Well, I think we've addressed most of the questions here. Again, there's a couple questions that are specific to the Petasense system, so I'll reach out to you each individually to answer those. But I'd like to thank Don and Laura so much from APS for joining us for the webinar today. This is the first time we're doing this, so we'll probably send out a quick survey to each of the folks that joined us to get their feedback, and hopefully we'll be able to do more webinars like this in the future. But thanks so much, Don and Laura. Have a great rest of your day.
Okay.
Thanks, Jeff.
All right. Thanks, everybody. Thanks for joining.